Hi, everybody. In the last lecture, we talked about answering a question using data and computation. There were 6 steps. Define the question with precise terms that can be true or false. Select a relevant data source. Define a feasible method that would definitively answer the question. Implement the method using some programming language. Evaluate and analyze the results, and then communicate the results. In this presentation, I'm going to talk about the second 2 steps, defining the method and implementing it with a programming language. Hi, this presentation is about going from the method to answer a question computationally to an algorithm to a program. So recall that step 3 in our procedure was to define a feasible method that would definitively answer your question. What we mean by a feasible method is a plan for solving a problem in which every step is feasible. So an example of a feasible step would be convert the street address to latitude, longitude coordinates, because there are known techniques and libraries of code for doing that. What would not be feasible is determine the street address from the house photo, because we don't know how to do that. An algorithm fleshes out or extends a method by it's a plan in which every step is described precisely. So for example, if our feasible step is convert the street address to latitude, longitude coordinates, in the algorithm, we specify what happens if the street address is a P.O. box number. Then what do we do? So the algorithm has to go into that level of detail. And then the program is an implementation of the algorithm in a programming language. So if we look at Nunberg's method as an algorithm, here's the method: finds mentions of politicians in the data set and looks at 7 words before and after the politician's name. We go from method to an algorithm as a sketch. This is not really what we mean by precise, where every step is precise, because there are some gaps here. But getting closer to a real algorithm, we would say, for each word in the data set, if that word is a name of a politician in the set of conservative politicians, then if a conservative label is in 7 previous words or 7 following words, then we increment the labeled counter for that politician. Or if it is a name, if that word is a name of a politician in the set of liberal politicians, if a liberal label is in 7 previous words or 7 following words, then we increment the labeled counter for that politician. So as I said, this is a sketch of an algorithm. It needs some fleshing out. So before we would write a program to implement the algorithm, or as we would write it, we need to further specify certain parts of it. For example, how to identify the politician's name. Nunberg used Boxer as one of his politicians, Senator Barbara Boxer. The word Boxer, we're going to find the word Boxer all over the place in the media. How do we know if a particular word, Boxer, means Barbara Boxer, or else just some boxer in a boxing match? It's feasible, but it's not necessarily easy, and we need to know how to do that. Likewise, what are the different labels for conservatives? Is it just the word conservative, or do we also include right-wing, right-leaning, traditionalist, whatever synonyms we may come up with for the label conservative? Likewise for liberals. Left-wing, do we count left-wing, left-leaning, progressive? So what I gave earlier as a sketch for each word, if the name of politicians and such conservative politicians, uh, this is not quite precise enough. We have to make it more precise. We have to answer certain questions. How are we going to do every step? A method, every step needs to be feasible. Um, so um, we think that's true with this algorithm, or with this method. So now we go to flesh it out as an algorithm, but we have to specify certain details before it really is an algorithm, before we can write a program. And we may figure these things out as we write the program. So if we look at our algorithm, so now let's talk about how we would flesh this algorithm out in a program. As we look at it, we can see a couple of different aspects. The algorithm has a couple of different aspects. One is what I might call the procedural aspect. For each politician, for each word in the data set. And the if the word is in the set of conservative politicians' names, or if the word is in the set of liberal politicians' names. So the for each and the if or if, that's what I'm calling the procedural aspect of our algorithm. There's another aspect, the data aspect, which is the entities we are dealing with. We are dealing with text. We're dealing with words. We're dealing with names. We're dealing with counters, counting how many times we see a label next to that politician's name. A programming language gives us a way to express both of these aspects. The first aspect is addressed by the control mechanisms the programming language offers. The second is addressed by the programming language's type language. The latter is where we begin with Python. We'll introduce Python's type language in the context of building an index. One way to look at a program is just as an input-output machine. It reads in a program, reads in data, manipulates it, perhaps combines it with other data, then writes out data, which in some way adds some value to the original data. If we look at the program implementing Nunberg's algorithm in this way, it reads in newspaper articles, lists of politicians, maybe lists of labels to look for, and outputs for each politician the fraction of times the politician was labeled. So if we adopt this abstract way of looking at a program, then let's talk about the kind of data you deal with in a Python program. And let's talk about that in the context of the problem of building an index. So it's a little simpler problem than the Nunberg issue, the Nunberg algorithm. We know what an index is. It's a listing of all the important terms in the book, and for each term, a list of page numbers where that term is found. Purely for readability's sake, when an index is printed, the words are grouped according to their first letter. Suppose we'd like to write a program that builds a book's index. The input for that program would be, looking at a program as an input-output machine, the input would be the sequence or list of characters that is the text of the book. Just imagine all the words, all the section headings, all the chapter headings. Imagine those as a single sequence of characters, because that is what it looks like to a computer when it reads it in. The output would be, the output of our index builder would be a list of pairs where the first element of the pair is a word, and the second element is a list of page numbers where that word is found. So we could visualize our program as first we take the text of the book, we send it into our index builder, which outputs that list of pairs. And then we send it to an index formatter, which does the grouping by first letter of each word, and then we send that to a printer. The actual program to do this is pretty complex because it has to break up the text into pages so that it knows what the page numbers are. So our index builder actually has quite a bit of complexity in it. We're only going to look at one aspect, which is how do we represent the input data and how do we represent the output data. One of the things a programming language is supposed to do is make it easy for you to work with data. A good programming language, a programming language that is fit to your purpose, does that. It makes it easy for you to work with the data that you want to work with. It does that in three ways. First of all, it distinguishes between different kinds of data. So you have numeric data, you have text data, you have image data, you have audio data. And the way it distinguishes is by giving you data types. So the second way is it gives you a decent set of built-in data types, ready-to-go data types. And then third, it gives you a way to construct new data types. It can't anticipate every kind of data that you want to work with, but it should give you a way to build a data type to work with that kind of data. So let's start with, when we talk about Python's built-in data types, of which it has many, let's start with three that the Python tutorial introduces in an informal introduction to Python: numbers, strings, and lists. So that is what you see. If you go to that link, you'll see in the example of using Python as a calculator, the tutorial will talk about numbers, and then it'll talk about strings, and then it'll talk about lists. I mentioned the word data type without introducing it properly. By now you know that it's different, refers to different kinds of data we deal with. Data type is one of the earlier inventions in programming languages. Inside of a computer, actually, there are no types. Everything is binary, zeros and ones. Data types were invented by the people who invented programming languages to protect you from making a mistake, like adding a number to a name, like taking two names and dividing one by the other, which doesn't make sense, or trying to capitalize a number, which also doesn't make sense. Python will tell you if you try to do arithmetic with a piece of text, you're making a mistake. Or if you try to convert a number to all uppercase, that you're making a mistake. It can do this because it has the notion of data types. There's a data type for representing numbers. There's a data type for representing text. Certain things you can do with numbers, certain things you can do with text. And as an aside, it's surprising to me anyway how much of programming language technology is about helping you not make mistakes, helping you write correct programs. And so it indicates just how hard it is to write software. It's very complex. It's easy to make a mistake. So a lot of programming language technology is about helping you not make a mistake. These three types: numbers, strings, and lists, and how we'll use them to build our index. We need Python's numeric data type int to represent page numbers. In addition to int for representing whole numbers like page numbers, there is the float type for representing numbers with decimal points like percentages and measurements. A string is a piece of text. So we use a string to represent text, which can be a word with a handful of characters, or it can be an entire book or a library of books. We'll use a string to represent the text of the book whose index we are building, and we'll also use a string to represent each word in the index. The list we're going to use in a number of ways. A list can store a list of other pieces of data, which can be the numeric types, strings, or even other lists. We'll use a list to store first the list of page numbers for a particular word, like horse, 47. So the list of page numbers where we find the word horse, 47, 122, 144. And then we'll also use a list to represent the list of word page number list pairs, which is in fact the whole index. The index is a list. And we'll also use a list because we don't have a better way at the moment. We'll use a list to store each word page number list pair. We'll use a 2-element list. So the first element of the list is the word, like mechanic. The second element of the list is the list of page numbers, 18, 66, 87, 145. The list is a very versatile type. A data type is determined by its set of operations. So for numbers, we can do add, subtract, multiply, divide, as we would expect. And there are many other operations that a programming language supports on numbers, such as floor, division, exponentiation, modulus, and others. The string type has an even larger range of operations. Just listing a few here: capitalizing the string, capitalizing the first letter, lowercasing the whole string, uppercasing the whole string, replacing, creating a new string where certain parts of the original string are replaced with substitution, splitting the string up into parts, looking for a substring, many operations on strings. And then a list also has many different operations than what we do with numbers and strings. You can add to a list, you can get the first element of the list, get the last element of the list, get any portion of the list, and other operations. So that is another way to look at what a data type is. A data type is whatever is the set of operations that you can do on it. A data structure is something you build up using the built-in types as like the parts of the data structure. The index that we've been discussing is an example of what we call a data structure. So if we define the index data structure as a set of definitions, it's a list of word, an index is a list of word page number list pairs. A word page number list pair is a 2-element list with a word as the first element and the list of page numbers as the second element. This word page number list pair is a bit awkward. We have Python offers us a solution for that, but we'll defer that discussion for later. So now we have a way of expressing data, and any instance of that data, any particular example of a piece of data, we're going to call a value. In Nunberg's algorithm for determining label bias, there is a counter for keeping track of the number of times a politician was labeled. That's a value. And in this case, it's the value of a simple type, a number. Data structures or a more complex type like a list or a list of lists or a list of word list pairs. That's a more complex value. In the case of Nunberg's algorithm for the counter, we'll use one of Python's numeric types, int, to represent that value. As an example of a number, a specific type int represents whole numbers. How do we keep track of that value? We use a variable. A variable is a named storage location in the computer's memory. You can picture it like this. We have a picture of the storage location in the computer's memory, a little box. It has a value in it. In this case, that value is a number 0. And then that box has a name attached to it, the label counter. Let's talk for a second about the name. There are strict rules for how we name variables in Python and in every programming language. The variable name must be only one word, so there are no spaces. So you notice that label counter had an underscore in it. It was not 2 words. Variable names must be made up of only letters, numbers, and the underscore. Variable names cannot begin with a number. Within those rules, you have a wide range of ways that you can come up with names, but there are also conventions in Python that restrict what the kind of names you come up with, and they're pretty strong conventions. The Python interpreter will not complain if you go outside the conventions, but your fellow programmers will complain. So in variable names, all letters are lowercase, except for certain kinds of variables which are constants. We often use all uppercase for those. Words are separated with an underscore. So if we have a variable name like label counter, there is an underscore between label and counter. There are 2 things we do with a variable. We can assign a value to it, which means put a value into the variable storage location, or we reference its value. You must assign a value to a variable before you reference it. First time you assign a value to a variable, Python creates that variable in the computer's memory. So if you try to reference its value before you have assigned to it, Python won't find the variable, and so it will tell you. And the way it'll tell you is usually by crashing your program, so it's a pretty clear indicator. So here we see a little fragment of a Python program on the right side there. We see an example of an assignment. Label counter equals 0. That takes the value on the right-hand side of the equal sign, the 0, and it pushes it, copies it into the storage location that is named by the variable on the left-hand side. If we look at the next statement, label counter equals label counter plus 1, there we see the same kind of assignment statement that we saw in the first statement, label counter equals 0. But we also see on the right-hand side of the equal sign a reference to label counter. So in this statement, we see both an assignment and a reference. The reference, the way the assignment statement works is everything on the right-hand side is evaluated. The value is computed. We take which means in this case, we pull the value out of the label counter location, storage location, which is 0, and we add 1 to it, and then we store that value back into the label counter storage location using the assignment operator. So we have both referencing the label counter and then assigning a new value to label counter. Now I'd like to talk to, so now we've seen just two statements of a Python program. And so I'd like to talk, just step back for a minute and talk about the Python program as a piece of text. Because if you haven't programmed before, it will look unfamiliar to you, and it's good to understand a little bit about the way way a program is just as text. So a Python program is, first of all, a piece of plain text. Plain because it does not contain any formatting, as a word processor document does. So there's no italics, there's no bold, there's no big fonts, small fonts, just characters. And to run your program, you give it to another program called a Python interpreter. The interpreter, first of all, makes sure that your program follows certain rules called syntax rules, which are very rigid. And this causes a large part of the frustration beginning programmers often feel. It's necessary, but at the beginning, it's very frustrating. And actually, even for people who've been programming a long time, it can be hard to deal with sometimes due to the nature of Python. So first of all, a few of the syntax rules. A Python program contains statements, generally one per line. If a statement extends to more than one line, you have to tell Python about it. Statements cannot simply wrap to the next line like a sentence in a word processor document. Not every line is a statement. Some lines are comments and are not considered part of the program. Indentation matters a lot. So we'll see examples in this little program here. The first two lines are comments. They begin with the pound sign or the hash sign. That's how you, everything after that, when the Python interpreter sees that hash, the pound sign, it ignores the rest, everything else on that line. And then it just goes to the next line. So the first two lines there are comments. Under the with statement, the third line in the program that's not a comment line, with open sys.argv1, you see everything under that is indented. That means that everything that is indented under the with belongs to the with. It's a block. What that means depends on what that statement is above it, but it belongs to that with statement. If it were not indented, then it would not be part of the with block. We see that again in the 4 lines after that, 4 row in header. Now we have the next 6 lines are indented. So those 6 lines belong to the for statement. And we also see a very long line. In the very last line of the program, the print statement, it's a very long line that extends beyond one line. And so that is, you have to know when that is okay and when it's not. So these are just 3 of the syntax rules of Python. So the first one, the comment. Text in a program that you don't want considered part of the program, like an explanation or a reminder to yourself, is called comment. In Python, anything following a hash sign up to the end of the line is a comment. So these are, the first 2 lines are comments. Indentation, as we saw, is meaningful. It's not just a formatting thing as it is in a word processor document. In Python, it's a meaningful part of the program. Statements begin in column 1 unless they belong to the statement above them. If they belong to the statement above them, then they begin at one indent level from the statement above. You can indent with a tab or spaces, but you cannot use both in the same indented block. So this is showing two examples of indentation. Long lines. In general, Python assumes that a statement is finished with the end of the line. If you really want a statement to spread over multiple lines, there are two ways. The first way is to use a backslash character as the very last character in the line. The second way is to leave a parentheses unclosed and then close it in a following line. So that's the example we followed. That's how this print statement goes across two lines. There is an unclosed parentheses. In fact, two of them are not closed. And then in the second line, they get closed. This is not very user-friendly, so it's really best to avoid long lines in Python. It can be difficult when you have a problem, and it has to do with line not closing a long line. The error message is confusing. The Python is as text can be kind of confusing. The rules for text programs, the syntax rules can take some getting used to. You'll wonder why your program is not working, and it's because Python is either not telling you have a mistake and doesn't look like a mistake to you, or it's interpreting your program in a way that you didn't expect. Gradually, you'll learn to read your program as the Python interpreter does, and you'll spot the syntax errors yourself without the interpreter having to tell you about them. And that's good because the Python is actually, the interpreter is not very good about telling you what is wrong. It'll tell you where it got lost, but it can't really tell you, except in some cases. In general, it can't tell you what you did wrong. It just can tell you where it got lost. Until you do develop that familiarity with the syntax of the Python program, just be prepared for a little frustration.